And hello, welcome back OpenFoamers. Welcome to this video where we're going to continue our discussion and debug the snappy layer experimental case for a hot sphere in oil. Okay, so in the last video, we kind of determined that the possible reason for error is that the mesh is not fine enough. Okay, so we want to change the way that the mesh is structured, right? And we already did our little test where we had the heat transfer coefficient value kind of checked from 2 seconds all the way up to 100 seconds. And what was the mesh like? It was a pretty coarse mesh. Okay, so I'm going to delete this. Let's show you what the mesh is like again. Okay, so we have the temperature. I'm going to use a slice plot. Okay, wireframe. Slice plot should show temperature. And let's use surface with edges so that we can see the plot properly. So okay, this was the mesh, and if we use the velocity profile, we will be able to see the magnitude of velocity, and we'll be able to see the solid region and the fluid region. So apparently here there's not much convection going on. And the possible reason why that might be is that the meshes, especially here in this region I'm circling, the meshes in that region I'm gonna go to paint. Mesh in that region is maybe too coarse, so it's not fine enough. Or if it's too fine, then you may have some stability issues, but at present it's not fine enough. So how would it work? Technically, you would conduct heat to a boundary layer over here, a boundary layer. Okay, and the region immediately outside the boundary layer is the highest velocity. Is the region with the highest velocity. So the boundary layer needs to conduct heat into this region. So the boundary layer needs to conduct heat into this region in order for this region to move. However, of course, if the mesh is so thick, this boundary layer that is being circled here may be very thick, and so as you know, there's a no slip condition here at the surface. At the surface here, there is a no slip condition, so it kind of slows this whole cell, the velocity of this whole cell down. So maybe the way to go is to have a smaller mesh so that this boundary layer region immediately adjacent to the sphere and immediately outside the sphere is better resolved, so that there's more movement. And the way to do that is to, of course, adjust snappy hex mesh. So, okay, I'm gonna, these are the results before. Again, there were some discrepancies as expected, but we can do things a little differently. So, first, let's go to System Snappy Hex Mesh. Okay. So we have two things to play with. We can play the sphere to oil and the oil to sphere. So the oil to sphere, this one, which I'm highlighting now, this is the fluid region. So we want to resolve this area better. So how can we do it? We can actually use more surface layers, and hopefully the smallest surface layer will be how do you say? Yeah, the smaller surface layer will be closest to this sphere, and hopefully it will be thick enough. Now, how is the thickness determined? Well, if you've done snappy hex mesh enough, okay, we will take note of this final layer thickness first. If we set it up that way, that we want, if we have a relative sizes is true, so it will take, okay, let's say the undistorted mesh directly outside. Okay, if your relative thickness is 1, then what OpenFoam will do is that, okay, it says that the layer I'm creating, it will be about this thickness. Okay, so I will take the undistorted mesh, and if the relative thickness is 1, okay, it is the size relative to this final layer thickness is the size relative to the size of the undistorted mesh, if and only if you select the relative thickness option over here, the relative sizes option. Otherwise, you'll be given absolute numbers, and this will be actually 1.3 meters. But no, we say it's one time the thickness of this relative thickness thing. So okay, so this is what it will do, and then this expansion ratio is the relative size between this this layer and the adjacent layer next to it. Okay, so if they have an adjacent layer next to it, so this is supposed to be, if this is thickness T, this thickness should be 1.3 T, thereabout. Okay, so and then the next layers will be more and more thin. They get thinner and thinner as they go towards this this layer here. So you can see this is the undistorted mesh. This is the first layer, second layer, and third layer. So you can see over here, this is actually 1.3 times. If you go from here to here, it's 1.3 times thickness. So how thick is the layer addition over here? Okay, the layer thickness is the sum of how many layers you're adding. Okay. Okay, let me bring this. All right, so the thickness here, I mean the total thickness of the layer addition, it will be the sum of all the layers together. Okay, so if there's 3 layers, you will have this first layer of thickness, and then you have this second layer, and this third layer, which is, of course, the ratio between here and here is 1.3. If you have 10 layers, go smaller and smaller and smaller. So that's how you control the thickness of your layer addition thing. So it will get thinner, right? So that's how thick your boundary layer here will be. Okay, so if I were to add 10 layers, here, okay, then yeah, I will get the resolution I want. So let's try that. We'll clean this up because we already have the data we wanted, and we know that that's not the case. That's not the way we want our thing. We don't want our mesh to be like that because it's not giving us the results, and there's no plume that's rising, so we can do an all run 0n. Oops. PS and A, I want to kill the process. Kill 301. Terminated. Okay, we'll do all clean again. And what I wanted to do all run 0 pre. Okay, so all run 0 pre n. So this will just set up the mesh for us. Okay, all clean, all run 0 pre. So it'll go around doing its meshing jobs. Okay, you'll do its meshing jobs, and then we can check the mesh. Okay, let's check the mesh of this new one. Okay, remember the old one was about like that. We can just take a snapshot before the data is, data is still here, but before it's deleted, we can take a snapshot. Okay. Let me see. Snipping tool? Yeah. So this was the mesh before. And then we can put it here. Okay, just ignore everything here. So we can put it here. You can see the mesh is about this size. And we can see the after effect. Okay, where is it? Yeah. Okay, so this should be done. We can take a look at the mesh size. So we just do a reload. Yes, you can see the mesh size is much finer there. Okay, so I do a side-by-side comparison. Of course, it's the best. And of course, I want to do it in Paint as well. Right? Look at ParaView. Okay. Okay, and I'll paste it into Paint. Okay, so can we see how this thing works? This is the undistorted size. First layer, second, third, fourth, fifth, sixth, seventh, eighth, ninth, 10. So this layer nearest to the surface is very, very thin. And that helps us to resolve the boundary layer we are talking about. Of course, we can, play around with these sizes. Instead of using an expansion ratio of 1.3, we can use 1.1, 1.05, and that will change the mesh accordingly. So okay, left expansion ratio 1.3 and 3 layers, right? On the right, we have expansion ratio 1.3, 10 layers. And we can actually, do a little more tweaking. If you don't want the first layer to be so thin, we can also do some changes. But before I go on to that, we can test the effectiveness of this mesh. So let me show you. I have it in my experimental case. So the experimental case is just a case where I do, I just run experiments for different meshes or different settings and see how well they work. So I don't waste time trying to figure things out on this video and see what happens. So I did this like behind the scenes. Okay, so with this mesh, with this mesh, I actually tried to run a simulation, and this is what happened. I can show you the experimental case, and I show you this. I show you the slice plot as well. Slice plot. Okay, I'm going to apply it, and slice plot should show you and show wireframe. Maybe surface with edges, and you'll see what the plot is like. You can take a look at the temperature. So you can see clearly, with this thing, you can see clearly where the boundary layer has built up. Okay, so just now that was a custom temperature range from 300 to 320, so you can see where the heat affected zones are. You can see over here, over here the boundary layer the boundary layer is very nicely built up. Okay, so test with mesh on the right is like that. You see the temperature profile, 300 to 320 Kelvin range. So the boundary layer is like this, and if we were to use normal what do you call that? Normal scale, the temperature scale, we can see this is what the sphere would look like. More interestingly, we want to take a look at the velocity as well. So this is what the velocity profile looks like. Okay, so the main area where the velocity is highest is right above the sphere, and this time we can see a nice plume, a thermal plume here. So this is very important. You have to get your you got to get your mesh right. So you see the velocity profile here, and you see the plume developing. So it means that we set up our case pretty right, in the sense that it at least has a plume. Unlike the last case where even at 1000 seconds, the temperature was stuck at 350 degrees Kelvin. So there's something wrong there. So this time around we have a plume, and that's a very encouraging news. Okay, so we can take a look at the system, post-processing, average heat transfer coefficient. Take a look at the zero directory. Okay, maybe I use a notepad instead. Okay, file open from the desktop. I'll go into here, CHT multi-region, OpenFoam Heat Transfer YouTube. And now we can take a look at the experimental case. So this was the case I ran. Post-processing oil, average heat, sphere heat transfer coefficient, and all files, surface field value. Okay, so this is where we get our data. So, okay, find mesh with 10 levels of layer addition. So we see that the plume is observed. Okay, so plume is observed. That's great. Let's changing the mesh to 10 layers of addition, we get a plume. Solved. Okay, so that's what it takes to get the plume right. Okay, so next thing, at least for this, changing the mesh does help, and I did the experiments behind the scenes. It works. So yeah, the thing is, just change the mesh and run CHT multi-region foam again. You should be able to get the same results. Okay, so next thing I want to get is, you know, all the data of the heat transfer coefficient and start to plot them. So I'm going to open the other one. Okay, the 100, and I'm going to put all files, surface field value. Okay, and that should do it. Goes all the way to 1000 seconds. Okay, so I'm going to get this tool, I'll paste it here, and this one will be equals to negative of G10, which is that. So I can turn it positive at least. So now I can see the trend of the heat transfer coefficient with time. Alright, and then we give it a comparison with the last one. Okay, so it looks like this. Okay, the heat transfer coefficient kind of bottoms out somewhere here. Okay, and if you were to look at the temperature even, heat transfer coefficient and temperature, it is, you know, the higher temperature you have, the more heat transfer coefficient. But this one's the one that goes with time. It doesn't have the sharp peak that we saw here before, and that was probably due to a meshing error. Okay, over here instead, the heat transfer coefficient stabilizes after a while, and that's what happens. Okay. So we have an exponential drop in temperature. Exponential drop in temperature as usual. At least the shape looks right. But problem is this. Okay, problem is this. If you were to take a look at the correlation, okay, I'm going to change it to general. Okay, if we take a look at the correlation, let's see the heat transfer coefficient at somewhere about 400 degrees Kelvin. Okay, 400 degrees Kelvin is about 237 seconds. Heat transfer coefficient is about 47, yeah, 44, sorry, 44.7, about 45. All right. So at 400 degrees Kelvin, the heat transfer coefficient in our coarse mesh case was about 63, and even that actually that happens to decrease the average Nusselt number. So while in the beginning we have a nicer you know, heat transfer coefficient which might match the Reynolds, which might match this Rayleigh number much better, because this Rayleigh number has a Nusselt number what do you call it? Nusselt number about 5 times that of the coarse mesh. So the heat transfer coefficient should be about 5 times higher than, let's say, this. So yeah, that's here. So we do have a very high initial heat transfer coefficient, which is great. However, it steadily drops off as the plume starts to develop, and it stabilizes around 44 or 45 actually. Alright, so it stabilizes around 45 over here, and it stays pretty much like that throughout the whole the simulation. Okay, so what could be wrong? Okay, well, let's take a look at surface with edges and see one plausible problem that might be going on with this simulation. Okay, if you notice carefully the velocity plots here, all right, the velocity is such that over here it's, I mean, at the surface, at the closest to the surface, yeah, it's bluish color. Closest to the surface is bluish in color over here. So okay, maybe I will do a snipping tool and go on the pint. Yeah, closest to the surface. Yeah, closest to, okay, one more zoom. Yeah, closest to surface, it's really bluish in color. I mean, not because of the lines, but the velocity is the lowest. Over here, you have a region of higher velocity. Over here, you have a region of highest velocity. Highest velocity. Now, the convection is such that the fluid will flow along this boundary and it'll go up here, right? So the rate of heat transfer will be determined not just by how quickly heat is conducted away from the sphere into the boundary layer and how quickly it's conducted from this immediate boundary layer into like some convection zone. It is also limited by how quickly the fluid over here, just above the sphere, gets out of the way so that new fluid over here can rise here. And that also will be determined by the mesh size. So apparently you probably want the mesh over here, the mesh here, to be refined. Now, question is why? Okay, so picture yourself having a fine mesh, and here, and let's say the temperature in each of these meshes is as follows. The central one is 450K. The rest are 380K. 380K. And suddenly we have a recombination. We have a large mesh size. Okay, you have a large mesh size. So, I mean, in terms of convection, usually the highest temperature, the high temperature fluid will rise up faster than, let's say, this lower temperature fluid. But once you get into this large mesh, all these things, may mix. They will undergo mixing. Why? Because this large cell is only described by one temperature. Cell described by one temperature. So the cell, what temperature will be this cell? It will be a combination of all these temperatures going in. So this cell will have one representative temperature, and that kind of is equivalent to what we might think of as mixing. So there is some mixing that happens if you have this large mesh here as compared to the fine mesh over here, so that this small little plume cannot get out of the way fast enough. Now, as a result, the overall convection rate may slow down because of this coarse mesh over here, and that is something we need to deal with. So in the next video, we want to talk about the ways we can get this this mesh a little more settled. Okay, so yeah, thanks for watching. I'll see you guys in the next video. Bye bye.